Welcome to Spring LIB.
In problem 32 of chapter 14, we are given a simple harmonic oscillator, a horizontal spring system, that has a mass that is comprised of a box, right here, and then a little stone inside of that box. Simple harmonic oscillator without any friction. It's ideal spring, so no need to worry about that. But what's particular about this problem is that after some time, particularly when the spring system is at its maximum velocity, a stone is removed from the inside of the box. And so effectively what that's doing is instantaneously changing the mass of the system. Now the problem gives us many of the initial values, such as the amplitude of the initial simple harmonic oscillator, as well as the mass of the box and the mass of the stone, and then the spring constant of the springs in the system. And so first, the question is asking us, what is the period after the stone is removed? This is a pretty simple calculation because we know that the period is just 2 pi times the square root of the mass of the system over the spring constant. And so using that equation, we get that the period is equal to 2 pi times the square root of the mass, which in this case, the stone is being removed, so it's just the mass of the box, which is 5.20 kilograms, divided by the mass, or not the mass, but the spring constant, which is 375 newtons per meter. And so after making this calculation, we get that the new period of the system is going to be 0.740 seconds. Now it's asking us, what is the amplitude after the stone is removed? Now here's where things get a little bit more tricky, but just using a simple trick, it's very easy to make this calculation. Now what we know about the system is that when the stone is removed, it's at maximum velocity. So right here, it's at V max, we can say. And so all of its energy is kinetic, and so we're just changing the max. So we are changing the total energy of the system, but the velocity is always maximized at this point. And so before and after we remove the stone, this is where the velocity is maximized. It's just going to be at a different velocity this time. So we can equate the velocity max initial and the velocity max final. So V max initial is going to be equal to V max final, which means using this equation that amplitude initial, let's say A initial, times the square root of K, the spring constant which does not change, over the initial mass, is going to be equal to amplitude final, which is what the question is asking us to calculate, times the square root of the spring constant, divided by the mass final, which is going to be just the box and not the stone. And so after plugging in some values, we get that the amplitude initial is 0.075 meters as given, and we're multiplying that by the spring constant, 375, the square root of it, over the square root of the mass initial, which is going to be 5.2 plus 3.44, since it is the mass of the box plus the mass of the stone initially. And this is going to be equal to the final velocity after we remove the stone. So the amplitude final, which is what we're trying to calculate, times the square root of the spring constant, 375, divided by the mass final, which is the mass of just the box, which is 5.2 kilograms. And so after making this calculation, we get that the final amplitude, just by dividing both sides by this chunk, we get that the amplitude final is equal to 0.0581 meters, which is equal to 5.81 centimeters. Now finally, what the question is asking us is to intuitively be able to say whether the period is going to be increasing or decreasing after removing this box. So we could do this by calculating initially what the period was and seeing how it compares to the period afterwards. But we could do this simply just by using this equation. We know that the period is equal to 2 pi times the square root of mass over K, so it's dependent on the mass of the system and the spring constant. Now the only thing that's changing is the mass, of course. And so we can deduce from this equation that the period is proportional to the square root of mass, which means that as the square root of the mass increases, so does the period, and vice versa. So if the mass has decreased, that means that the square root of mass has decreased and that the period has decreased. So we know that the period after the removal of the stone will have decreased.